Hello, my name is Mason Cipollini with my partners Mackenna and Mayra Mendoza. This is the Fiber Lab for OPTI 471A. Optical fibers are a very common piece of optical equipment used to transmit light quickly and near perfectly over a distance. These fibers typically consist of a glass core and an outer cladding with a higher index of refraction. At the core cladding interface, a ray experiences a total internal reflection for angles larger than the critical angle. The critical angle is calculated using the arc sign of a cladding index over the core index. The critical angle is defined by the numerical aperture of the fiber, itself defined as the sine of the acceptance angle of a fiber. Using Snell's law, we use the formula shown to determine a fiber's numerical aperture. For the first experiments, we were given fiber patch cords with three connection types, FCPC, FCAPC, and bare fiber. We would connect the patch cords from the laser set at 80% output to a power meter and record each received power to determine how sensitive transmitted power is to coupling changes. Then, we would connect two fibers from the laser to the power meter using fiber mating connectors. We would measure the power received and calculate the loss from this connection and repeat with at least three other fiber mating connectors. All of this would be done in proper dB scale. From the sensitivity tests, we obtained the power measurements in the left table. The decrease in power from each patch cord is to be expected as the end faces of the FCPC to FCAPC have different angles, and the measurement from the bare fiber was bound to be imperfect. We could not achieve anything from the bare fiber adapter as we couldn't fully connect the bare fiber to the adapter. As for the connection tests, we collected and calculated the values in the right table using the loss formula below and the power measured from a single fiber as the reference. There wasn't much expectation for change here, so the second connector measurement was an outlier.
Fiber splicing is the process of melting and joining two fiber ends so they behave like one continuous fibers with almost no loss. To do this, the splicers need to align the fiber's cores longitudinally, laterally, and rotationally, and then uses a small electric arc to fuse the tips together. In theory, a good single-mode splice should have a loss below about 0.1 decibels, but this depends completely on the alignment and accuracy. In our lab, we followed the standard fusion splicing steps, cutting 1 meter fiber, cleaning it, and cleaving both ends to make smooth, flat faces. We loaded both fibers into the splicer and attempted to line them. Our cleaves were successful, but when the arc was applied, the ends burned or misaligned, and the machine couldn't complete the fusion. This is usually caused by calibration issues, incorrect arc power, or damaged alignment systems, which explains why we couldn't obtain a valid splice loss data.
Now I'm going to go over the optical isolator and the optical circulator and then compare our results to what we expected. An optical isolator is designed to let light pass in only one direction. In a forward direction, it has low loss, but if any light tries to travel backward, the isolator introduces very high loss. This prevents reflections from reaching the laser and keeps the system stable. A circulator works a little differently. It's a 3-port device that routes light in a cycle from port 1 to port 2, from port 2 to port 3, and from port 3 back to port 1. In our measurements, the isolator showed around 28 decibel forward loss and over 40 decibel in reverse, which agrees with the expected strong one-way behavior. For the circulator, we saw directional transfer on 1 to 2 and 2 to 3 and almost no detectable signal in the reverse paths, which confirms that the circulator routed light exactly as intended.
I really enjoyed observing the impacts of fiber connection types. I do research with fibers, so being able to observe the impact of asymmetrical fibers helped me better understand the benefit of solely using one type. What I did not like was using the provided fiber splicer, as the initial arc was far too powerful and did not allow anyone in our lab section to splice successfully.